Welcome to The Explainer. Today, we're going to unlock the secrets of physics hidden in something you do pretty much every single morning, making a cup of coffee.
So, let's kick things off with a question that seems almost too simple. You've seen this a million times, but have you ever stopped to wonder why? It seems obvious, right? But that why? Well, that's where all the cool physics is hiding.
See, the answer isn't some simple one-line explanation. It's actually a really fascinating journey through the hidden world of heat. Think of this as our map. We're going to cover the difference between heat and temperature, see how stuff, reacts to getting hot, and finally, we'll look at the three main ways heat gets from one place to another. All right, let's get into it.
Okay, first things first. To really get this, we need to understand the two main players in our little story, heat and temperature. And here's a spoiler for you. They're absolutely not the same thing, even though we talk about them like they are. Yeah, we throw these words around all the time, right? The heat is high, what's the temperature? But in physics, totally different. The easiest way to think about it is like this. Heat is the actual energy that's on the move, flowing from hot to cold. Temperature, on the other hand, is just the measurement of how much energy is in a thing. So heat is the cause, and the temperature you read on a thermometer, that's the effect. All right, so what happens when we start adding heat to stuff? Well, things start to change. And one of the most obvious, most visible changes is something called thermal expansion. And I bet you've actually used this without even realizing it. Ever had a super tight jar lid? You run it under hot water, right? Bam! That's thermal expansion in action. The hot water makes that metal lid expand just a little bit, just enough to loosen its grip on the glass jar. You're literally using physics to get to those pickles. How cool is that? And this right here shows the simplest kind of expansion, what we call linear expansion. Basically, as things get hotter, they get a little bit longer. It's the whole reason engineers have to leave those little gaps in railway tracks or on bridges. They know that on a scorching summer day, that metal is going to expand, and if it doesn't have room to grow, it's going to buckle. It's a huge deal. But here's the thing. Not all materials heat up at the same rate. Some are like sponges for heat. They can soak up a ton of energy before their temperature actually starts to rise. And this property has a name: specific heat capacity. Water is the superstar here. It has a super high specific heat capacity, and you know this intuitively. It's why it feels like it takes forever to boil a pot of water on the stove. And this special property of water is absolutely crucial. It's what makes it such an amazing coolant. Think about it. A little bit of water can pull a massive amount of heat away from a car engine without getting crazy hot itself. That's why we use it. It's an incredible temperature regulator, not just in our cars, but all over our planet. Okay, so heat can make things expand, but it can also do something way more dramatic. It can make matter completely change its state. We're talking solid to liquid, liquid to gas, the whole shebang. And trust me, this is where things get really, really interesting. So, let me ask you this. Picture a block of ice melting. You're adding heat to it, right? I mean, that's why it's melting. But what's happening to its temperature while it's turning into water? Does the thermometer reading actually go up? The answer, and this might surprise you, is no. The temperature stays parked right at 0 degrees Celsius the entire time it's melting. All that heat energy you're adding, it's not raising the temperature. It's busy doing a different job, breaking apart the bonds of the ice crystal. This is called latent heat. You can think of it as hidden heat. And it's the exact same reason sweating cools you down. As the sweat evaporates, it uses latent heat, literally pulling that energy right off your skin. So, how do scientists keep track of all this? Well, they use maps like this one. It's called a phase diagram. It looks a little complicated, but all it's really doing is showing you what state water will be in, solid, liquid, or gas, at any possible combination of temperature and pressure. And check this out. See that one little spot on the map, point C? That is the amazing, the mind-bending triple point. It is one very specific, very precise set of conditions where water can exist as a solid, a liquid, and a gas, all at the exact same time, in perfect balance. I mean, how wild is that? It's like something straight out of science fiction. Okay, so we've got our clues now. We know about heat versus temperature. We know about expansion. We know about state changes. It's time to go back to our original mystery. Let's solve this thing. How does the heat get out of the coffee cup? So here's the most important part. Heat doesn't just vanish into thin air. It has to travel. And it turns out there are three main ways it makes its escape from your coffee cup out into the room. First up, we've got conduction. This is basically heat transfer through direct touch. Imagine a line of dominoes. You push the first one, and the energy travels all the way down the line. That's conduction, energy moving from one molecule to the next. So in our coffee example, conduction is the heat traveling from the hot liquid through the solid ceramic of the mug to your hand. It's also the reason that metal spoon you left in there gets hot all the way up the handle. The heat is literally conducting its way up the metal. All right, number 2 is convection. This is where heat gets a little cleverer. Instead of just passing energy along, it hitches a ride on a moving fluid. And by fluid, I mean a liquid or a gas. The hot stuff itself actually moves, carrying the heat energy with it. And for our coffee, you can actually see this happening. It's that steam rising from the top of the mug. The hot coffee heats up the air and water vapor right above it. That hot air is less dense, so it rises up and away, carrying a whole bunch of heat with it. And last but not least, we have radiation. Now, this one's different. It's heat that travels as invisible electromagnetic waves, specifically infrared waves. It doesn't need to touch anything. It doesn't need to ride on any fluid. It's exactly how the heat from the sun gets to us across the empty vacuum of space. And believe it or not, your coffee mug is doing the same thing. It's constantly radiating heat out into the room. You can feel this yourself. Just put your hand near the mug without touching it. That warmth you feel? That's radiation. The mug is literally broadcasting heat waves in all directions. So there you have it. The mystery is solved. Your coffee cools down because of a team effort: conduction, convection, and radiation. But here's where it gets really big. What if I told you that these exact same principles don't just explain your coffee, they explain our entire planet? Seriously, could the physics happening in your tiny little mug actually explain something as massive as the weather? The answer is absolutely yes. Think about it. That same convection that makes steam rise from your coffee cup, on a global scale, that's what creates wind. The sun heats the land, the hot air rises, and cooler air from the ocean rushes in to take its place. That's a sea breeze. Scale that up, and you get global trade winds. You even get massive seasonal patterns like monsoons. It's all just convection. And what about radiation? Well, that explains why you wear light-colored clothes in the summer to reflect the sun's heat and dark clothes in the winter to absorb it. It's the same principle. From your coffee mug to your closet to the weather outside your window, these rules of heat transfer are everywhere. So, the physics of a simple cooling coffee cup is really the physics of our world. It's happening all around us. Now that you know the rules, what other everyday moments are you going to see in a totally new light? What are you going to notice differently tomorrow morning with your coffee?